Hi, everybody. I decided to go ahead and finish the solution of the exercise that we started on at the end of the last screencast. So remember, this was the exercise where x is some normal random variable with mean zero and variance sigma squared, and you're wondering about the distribution of the square of x. So that random variable is called w. Well, we do know that if we take x and multiply by the constant 1 over sigma, we get another normal random variable, and its mean would be still 0, but its variance would now be a 1. Okay, and so we know that we know the distribution of something kind of close to w. We know the distribution of the w over sigma squared. We know that it would have to be chi-square with 1 degree of freedom, because the square of a standard normal is chi-square. That doesn't quite give us the distribution of w, because w is sigma squared times a chi-square with 1 degree of freedom. But we can get it. I'll go ahead and get us a little bit more that we might find useful along the way. After all, chi-square is a special case of a gamma. It's where it's a gamma where you set the alpha equal to 2 and the theta equal to r over 2, like r is your degrees of freedom. So why don't we just go ahead and find the distribution of any positive constant times any gamma. Okay, so let's see be a fixed positive number. And what should the distribution be? Now, intuitively, think about this intuitively before we do all the math. If you consider gamma to be how long to wait until the alphath event, where on average you gotta wait theta units of time between events, then multiplying the waiting time by c, it sounds to me like what you're really maybe doing is switching to a process where everything happens c times as slow. And so instead of waiting theta on average between events, you're waiting c times theta between events. So I'm going to hazard the guess that the distribution of c times a gamma alpha theta is actually going to be another gamma waiting for the same number of alpha events, but your average waiting time between events is c theta. Well, let's see if we can verify that guess mathematically. So we let x be gamma alpha theta. Let's let y be c times x, and we need the moment generating function for y. So it's e to the expected value of e to the ty, which is expected value of e to the c times your capital X. And so that's the moment generating function of x at the value ct. And the moment generating function for a gamma is 1 over 1 minus theta t to the alpha. And so you just stick in a ct instead of a t. And whoops, I left out the t there. It's supposed to still be there. And so we would have a 1 over 1 minus c theta times the t that, is supposed to be right there. I wonder if I can actually put it there. I don't think I can. I have to have the paying version of Adobe PDF. So imagine a t right there. And so you stare at that and you realize, oh, wait a minute, that has the form of the moment generating function for a gamma random variable. Alpha is just the same as before because the power is just the same, but now there's a c theta next to the t instead of just a theta. So it's a gamma alpha c theta random variable that we're looking at. So we've confirmed it. Constant times gamma is gamma, same shape parameter, multiply the expected waiting time by c. So specializing down to a chi-square, we get that constant times a chi-square is going to be chi-square with c times the degrees of freedom. And so since w was sigma squared times a chi-square with 1 degree of freedom, then W must be chi-squared with sigma squared degrees of freedom. So that's my thinking on this problem. See ya later.